first of all, I want to make sure that you understand what you're given on your formula sheet when it comes to the equation of a line in vector form. Okay? We're going to be dealing with lines both in 2 dimensions and in 3 dimensions. But let's look at some basic equations of a line. Now, what we're talking about here, as an example, is we could have a velocity vector, and if it's moving at a constant velocity, that would be kind of like our slope, right? And if we're in 2 dimensions, it relates directly to our slope. But if we're in 3 dimensions, that's still kind of like a slope. And then the line will tell us our position at different times then, okay? The equation that's given in your formula booklet is this. Vector R equals vector A plus T times vector B. Okay? This is a form that you need to be familiar with because that's what you're going to see in your formula booklet if you happen to look at it. Okay? And this is a basic vector equation. So let's talk about what we're looking for here. R is a position vector. Okay? R is the position vector. What's our position at a given time? Okay? So R is our position vector. A is our position at time 0. Okay? It's a position vector. Again, it's if we don't say a position vector relative to a certain point, where is that vector in reference to? Our position in reference to the origin. Okay? So this is going to be like the coordinates of a point, but it's a position vector in relation to the origin. A is our starting position vector in relation to the origin. And then T represents time. All right? B is our velocity vector. Okay? B is the velocity vector. Now, because it's given in this form, our velocity vector is going to need to be in terms of a horizontal and vertical component. Okay? We can't try to deal with a velocity vector that's like 50 miles an hour at 16 degrees. Okay? That won't make sense when we're relating this to position vectors. So if you're given a velocity vector that has, where they give you the magnitude and direction, you'll need to figure out the components. And we'll talk about that. Okay? More trade. All right? Now, if we were to write this out in component vectors, kind of rather than using R, A, and B, if we actually wrote it out, we could write it this way, okay? Our position XY, or XYZ if we're in 3 dimensions, is going to be X sub naught, Y sub naught. That's our horizontal and vertical position at time 0, plus T times this velocity vector AB. Okay? X sub naught, Y sub naught is the position at time 0, T is our time, and AB is the velocity vector. Okay? So, here's a tool that we can use that will really help us use these vector equations. Okay? And they're what are known as parametric equations. All right, I'll let you get caught up here for a sec. I know right now we're just covering a lot of the background info that we've got and terms that we've got to know before we can actually use some of this stuff. Okay. All right. At the root of this word parametric, you can see the root word parameter. All right. Parameter. All right. And basically what we're breaking this down into is two different equations, or if we're in 3 dimensions, 3 equations. And it'll kind of break it down by parameters, horizontal, vertical, if we have a 3rd dimension, that one as well, okay? So what we would do here for our parametric equations, notice here in the component vector form, x comes first, and then these are vectors, right? So we could do vector addition. So watch this. If I do vector addition, I would have x sub naught, y sub naught, plus at, bt. All right? So there's my constant multiple of that vector. And then if I continue to add the vectors together, I would have x sub naught plus at, y sub naught plus bt. So basically we just took this component vector form and we used vector addition and scalar multiplication to get it all into one nice vector. And the reason why that's nice is because x equals x sub naught plus at, and y equals y sub naught plus bt. And the reason why this is helpful is because it actually allows us to isolate horizontal movement or vertical movement. Okay? We can focus in just on the horizontal or the vertical. This is used frequently like in projectile motion. Here we have this projectile going through the air. We have some barrier that we want to make sure that we clear. Okay? So if we know our horizontal component, we could say, okay, how far away is the back edge of that barrier horizontally? And if we know how fast it's going horizontally, we could figure out exactly how much time it's going to be in the air when it reaches that point. So we're just looking at the horizontal. Then once we get that time, we could plug that time into y and make sure that y is somewhere above however tall that barrier is. Okay? So if it took, 5 seconds to get this far horizontally, then we would plug 5 into y and make sure that whatever that equaled was greater than this. Okay? And if it's not, then we have to adjust our targeting or something.
I was actually one of those like 2 days ago.
Oh yeah?
I just had a quiz on projectile motion.
Oh, okay.
I mean, the formulas are like derived from these.
It's kind of like,
Yeah.
it's the same thing, but like this is a different way of thinking about it.
So let's think our way through a little bit. Okay, here's a vector equation in component form. So let's just try to identify a few things here. Okay? We have this vector equation, xy equals -2,5 plus t times 2, -1. What would our starting position be in this case? -2,5. Okay? -2,5. That's our x sub naught, y sub naught. Okay? what would our velocity be?
2,
It would be 2, -1, okay? So using our notation here, r equals a plus tb, alright? A plus t vector b. This would be our vector A, starting position. Our velocity vector B would be 2, -1. Okay? But now we can write our parametric equations. X would equal,
-2 plus 2.
there we go, -2 plus 2t.
Bye.
See ya. Do well in your race.
Thank you. Take care, man.
And then we have y equal to,
-t.
5 minus
yeah, 5
5 minus t.
minus the t. Okay? And you see what we just did now is now we can break it down so we're just looking at the horizontal or we're just looking at the vertical. Okay? Now, finding points is simply a matter of plugging in different times. Okay? Plugging in different times. So, when t equals 0, where are we?
-2 or 5.
-2, 5. Now, one thing that you should get into the habit of doing, if you're graphing these, thanks, you too. Put the time next to the point. Okay? Put your times next to the point. So, there's our time equals 1. Where would we be when the time equals 0? Where would we be at time equals 1?
0, 4.
0.
Okay, 0, 4. Notice our velocity is 2, -1. Okay, so we're going to move forward 2 and down 1, right? See how slope relates when we're in 2 dimensions? Okay, or if we plug in 1 for t, we have -2 plus 2 times 1 is 0. And if we plug in 1 for t here, we have 5 minus 1 is 4. Okay, so there's at t equals 1, we're at the point 0, 4. Okay? The nice thing about this, and this is where the equations really come in handy, is we don't want to keep having to go over 2 down 1, over 2 down 1, over 2 down 1, over 2 down 1. We could now jump to, hey, where are we going to be after 5 seconds, or whatever our unit of time is? Okay, well, we plug in 5. X is going to be a -2 plus 10, and y is going to be 5 minus 5. So we're going to be at the location 8, 0. Okay? Okay. So 8, 0 is where t equals 5. So you notice here we have this path, this linear path. Okay? Now, this last one here is a little bit different. Okay? How could we have a negative time? Right? The whole way that we are able to look at negative time is kind of under a couple of conditions. Number one, if we know that whatever object we're looking at was traveling in the same direction with the same magnitude before we actually started the clock, we could look at negative time to see where it was. Okay, you're kind of going back in time. 0 for our time is somewhat arbitrary. Okay? Now, you may look at a problem where it actually is it's not moving at all, and then we're starting to move. and then you couldn't look at negative times. But if this were, say, a comet moving through space, and we're tracking its progress, we could go back in time to see where it was. You know, hey, where'd this thing come from?
Wouldn't it start at 0? Technically.
But you don't know until you start timing it.
Yeah,
Well, that's the
so
thing,
you
the-
go
When you
back
start
before you
timing, that's
started
not like
timing
when
it.
it's
Yeah,
the meteor didn't just show up when you started timing it.
You're almost like
yeah, we don't know where it actually started, so we can set an arbitrary time 0 and just kind of go back in time to see where it was. Okay? You know, so if we had known that this thing was moving along this path the whole time, then yeah, we could go back in time to -2, and it would be x equals -2 minus 4, and y equals 5 minus a -2. So we would have been at -6, 7. Four, 5, 6, 7. So we would have been right here. Okay? So sometimes you can look at negative times, but other times, depending on the situation, it literally started moving when we were at time 0, so looking at negative times wouldn't make sense. Okay. Now, another thing this allows us to do, and this is again where the parametric equations come in handy. Let's say we want to figure out when is this thing going to be crossing this line here? When is it going to cross where x equals 10? Well, if you're looking at the vector equation itself, that may be a challenge to figure out. Okay? However, if we break it down into the parametric equations, we can isolate this horizontal movement. When are we horizontally going to get to 10? So what would I do with that?
You solve for t.
We'd solve for t. We'd plug it into x and we'd solve for t. Alright, so x is -2 plus 2t. So we would set it 10 equals -2 plus 2t. And what do we get for t?
6.
We get 6. So now we can figure out, alright, well, where exactly are we at that point in time? And we would do that by then plugging 6 in for y. So y is 5 minus t, so y is 5 minus 6, which is a -1. So I know now this point must be the point 10, -1, and it happened when t equaled 6. Okay? That's like that projectile one I was just telling you about. When are we going to be where that barrier was? Alright, so what height are we at that time? We're isolating the horizontal and vertical movement in order to analyze it a little bit. To find out the when and then the where. Alright? Alright. Let's try a couple others. I'm basically what I'm doing is I'm trying to relate these equations to a few different kind of questions that we could come up with. Alright? So this first one is, what's the starting position? What's our velocity? What are the parametrics? Where are we at different times? Those are just basic questions. So now taking it a couple steps further, does this object actually hit this point 2, 3? Okay. Now, will x equal 2 somewhere?
Yeah.
Yes. Okay. will y equal 3 somewhere?
Yes.
Yes.
Yes. What's going to have to happen in order for this to go through the point 2, 3?
You do system of equations.
What do you mean?
Well, you could solve for t, so you.
You're right.
I mean, the horizontal and vertical components both have to go at the same time to meet a point.
Okay, and that's what you would find. Here's what Samantha said. She said, all right, well, x is -2 plus 2t. There's the x. And y, we would set it up equals 3 is our y, so 3 would have to equal 5 minus t. Notice our parametric equations, and then that's what Derek was saying. These two times
The same.
would have to be the same. Otherwise,
They won't pass.
we didn't actually hit that point, okay? So, you know, if we're graphing this, we know at some point x is going to equal 2. And we know at some point y is going to equal 3. But does that actually happen at the same moment?
Yes.
All right? And if you solve this, t would equal 2 here. You add that, that's 4 equals 2t. T equals 2 there as well. So, yes. Yes, that is, it does go through that point. Any questions about that? Okay. So, everything we've done so far has been 2 dimensions. Let's look at 3 dimensions. It's actually, like many of the things we've looked at with 3 dimensions, it behaves exactly like the 2 dimensions, we just have this third component that we have to deal with. Okay? So, instead of just x sub naught, y sub naught, it's x sub naught, y sub naught, z sub naught. Instead of a velocity of AB, it's ABC. And instead of just 2 parametric equations, we actually have 3 parametric equations. Okay. So same principles apply, we just have 3 of them now. All right, so here's a question that kind of ties today to earlier. How would we find the angle between those 2 lines?
Would you? Can you find the magnitude of the vectors and solve that way?
Which vectors would we be looking for?
The
What
x parameter and the y parameter, the vector.
Not those. What determines which way we're going?
The
The
velocity
direction.
vector.
Yeah.
The velocity vectors. So guess what?
It's just the velocity.
All you care about are these 2 vectors right
And
there.
you apply the same thing.
Find the angle between the 2 vectors using the formula that we already know, and you got it.
Gotcha.
All right?
Thank you. Have a great day.
All right. You too.